All right. Okay. Wow, this is bright. Ladies and gentlemen, welcome to my presentation entitled Protons and the Floating Water Bridge. I would like to use this moment to thank the organizers for enabling this wonderful conference, and of course, I'd like to thank Jerry for his very kind invitation, which gives me the opportunity again to present to you our latest research. And our research is about the interaction between high voltage and water. I'm quite sure that every one of you, at some point in your life, you have learned, don't do that. They're really not going well together. Because you know, when you're lying in the bathtub and the murderer comes and puts the blower, then you're dead. Or if you pour water onto an electrical machine, unless you don't want to destroy it, you shouldn't do that. So the question arises, if this is just dangerous and destructive, why should you deal with this? Why should you investigate this at all? Well, I would say this is actually a matter of perspective, because from a different point of view, for example, from the International Space Station, if you look down to our wonderful planet, you see that the interaction between high voltage and water is very common and very frequent, and that is lightning. Lightning is nothing else but the interaction between water in the clouds and water, let's say, in the ocean or another cloud. And I think if nature does something, it's worth investigating the principles behind this interaction, because there's nothing, in my opinion, that nature does that doesn't make any sense. And one of the peculiar interactions between high voltage and water is the so-called Electrohydrodynamic liquid bridge, also known as the floating water bridge. This is a phenomenon discovered in 1893 by Sir William George Armstrong, and it's very simple. You take two glasses, you fill them to the brim with chemically pure water, then you submerge two electrodes into this water, preferably made of platinum or some noble metal. And when you apply a high voltage, 15,000 volts DC, and provide a current of about 0.5 to 1 milliamp, then you get a watery connection between these two beakers, and if you now pull the beakers apart, this connection remains stable. Now, much more interesting than this animation is the actual formation recorded with a high-speed camera. You have the two beakers here. This is 120 times slower than in reality, and you see that after a short discharge, the surfaces of the two beakers start to move, droplets are ejected, jets are created. This is very well understood in the field of electrohydrodynamics, and in this chaos, at some point, a capillary bridge is formed between the two beakers. Now, once you have a watery connection and a current is running through, then this connection grows, it gains size, stability, it gets a real macroscopic phenomenon, and this watery connection is the floating water bridge, which I have been studying for the past 10 years. Now, if you look at this in real time, you see that the formation is extremely fast. And it's there, that's all. And as I told you before, we can now pull the beakers apart, and when we do that, interestingly, if this was just a capillary bridge, it would break now, but no, this connection remains stable. And even with the naked eye, if you look at it, you can already see that it appears to exhibit properties of both the solid and the liquid state. Naturally, to us, we're all scientists, this is not proof that this actually is something in between liquid and solid. I'm just saying it gives you the idea that there might be something more to this phenomenon than that's just a nice parlor trick. And by liquid and solid state, I mean liquid because obviously there's water flowing through this bridge, because you see the levels in the beakers are changing, and solid because it seems rigid and it doesn't fall down, it doesn't break. Now, if we want to know more about how the water is moving through this bridge, we just have to change the wavelength of the spectrum, electromagnetic spectrum, which we use to observe the bridge. So if we, for example, use thermography, where we visualize temperature, infrared radiation, we see that the bridge is heating up, and we see that the flow through the bridge is actually highly turbulent. It's not laminar. And if we magnify this, we can see that it seems to be, there are vortices on the outer shell, and there seems to be a hot core. So what is white here is about 40, 45 degrees Celsius. That is mixing with cold water that's circling around the bridge. Now the first question is, why is this happening? Why is the bridge heating up? Well, the answer is actually very simple. You have a current running through the bridge, 0.5 to 1 milliamp, and the bridge is naturally the part with the smallest diameter of the system. So it's like a fuse, or it's like the wire in your bulb. So if you calculate and simulate the current density, it's straightforward and it's very easy to do. You see that the current density in the bridge is, of course, highest. So this is where all the power, the electrical power that you put into the system dissipates, and this is where you create the heat. Next to the current, you can also very easily simulate the electric field, or more precisely, the electric displacement, which is the field in the medium. Now, what good does that do? How does this help us? Well, it provides us with a very simple explanation as to why this phenomenon is stable and why there is water flowing through the system at all. Because we all know water as a dipole is attracted to areas of highest field strength, meaning that there is a force that pulls water molecules or water as a substance out from the beakers into the bridge and from the bridge into the other beaker, and that force is present in both directions. Moreover, in case the bridge wants to break down, as is indicated in this simulation here, you see there's a gradient building up in the bridge which pulls it right back up. So from an electric field point of view, it's logical that this phenomenon is stable and that there is water flowing through the bridge. Now, are all questions about this phenomenon solved, since we know now why it's heating up and why it's stable and why there's water flowing through? Well, that again depends on how interested you are actually in the phenomenon. For example, we have seen, the bridge is heating up, but is that infrared radiation really heat, or how does it look like? For example, if we took a spectrum of that, would it look like water that is just 40 or 30 degrees Celsius? In order to do that, you have to compare it with the infrared emission of normal water. And here I give you two spectra of water of 37 and 47 degrees. Infrared emission spectra, we have here wave numbers against the emission arbitrary units. And what you can see here is both have a peak here around 2,300 wave numbers, and the intensity of the 47 degrees water is higher, of course, because it's warmer. Moreover, you see the CO2 absorption peak, which is very difficult to get rid of, even if you flush the system with nitrogen. You see the water vapor absorption, because at any given temperature above liquid water, you have water vapor, and so you have the very fine, sharp lines of absorption. And we have that now, and we compare it to the water bridge, we would expect that the curve of the water bridge looks the same and is somewhere in between here. And interestingly, it's not that easy. The first thing that you probably see when you look at the spectra is, and it catches your eye, is that this in the middle, this part is different. But this is the most unimportant part of the spectrum. Why? Because this is the water vapor. And the water vapor is not a part of the bridge, it's above the bridge. And we have calculated that the electric field is strong enough to accelerate ions in the air so that they can collide with the water molecules and excite them so they can emit instead of absorb. This is why the peaks go up. But this is just the vapor. Now, if we want to look at the bridge itself, we have to look at these two regions, 3 to 5 micrometer and 8 to 12 micrometer. And here, if you look at the lower end of the spectrum, you see that between 8 and 12 micrometers, the emission curve of the bridge is almost the same as that of water with 37 degrees, right? But if you look at the low wavelength range, 3 to 5 micrometer, you see first of all that the peak has shifted, and secondly that the intensity, the area underneath the curve, is, if anything, much more close to 47 degrees than to 37 degrees. That would mean that the bridge has two different temperatures at once, depending on which wavelength you choose. Now that is nonsense. That can't be the case. So when we found that, we thought we have to run a different independent experiment to confirm that this is true. So we took two thermographic cameras, sensitive in the respective areas, and if that, what we see here, is true, then one camera should give us one temperature and the other should give us the other. And as you might have expected, this is the case. We have here one thermographic camera, and you see here a little bit of the bridge shining up in the short wavelength range, and the other thermographic camera, which both have, of course, perfectly calibrated, doesn't show you the bridge at all, or a very faint image. Which means that depending on the wavelength, you get different result on the temperature. There's an additional non-thermic emission at shorter wavelength. It has to be, because the bridge can't have two temperatures at once. And we think we know now where this is coming from. We think this emission can be interpreted as a result from a protonic band transition. Now, solid-state physicists will say, whoa, wait. Band transition, protonic, what do you mean? This is a liquid, you can't have any bands in here. Bands are properties of the solid state. And why protons? You didn't tell us anything about protons. Yeah, well, I told you that there's current running through the bridge. And how can current be transported through water? Well, that's basic electrochemistry by electrolysis. So next to the liquid flow, we have shown that there's a gas flow. Hydrogen and oxygen are produced in very small quantities, but that's to be expected because the current is low. But next to hydrogen and oxygen, and this is interesting, in electrolysis you also produce protons and hydroxyl ions. Now, if you do that in one beaker, as electrochemists you don't even write that down because they immediately recombine to water. But if you do it in two beakers, then the situation is different, because then the mobility of the ions suddenly plays a role. Because it's very well known that hydroxyl is much slower in liquid water than protons are. Meaning that the recombination of these two doesn't take place in the bridge, it takes place in the catholyte beaker. Meaning that although water is running in two directions in the bridge, there's a monodirectional proton flow through the bridge at all times. So we have established we have electrolytic protons running through the bridge at all times. However, I also talked about the band transition. So if we were talking about something like that, we first have to find out what is the actual state of the bridge. Is it a liquid or is it a solid? And do we have hard fact science that can tell us what the state is? And yes, we have. We can measure the ultrafast vibrational energy relaxation of an H2O molecule. Why H2O? Because it's asymmetric, and as a spectroscopist this is beautiful because you can really excite just one bond, which is the HO bond in this molecule. And why would you do that? Because if you excite it, you can then measure how long does it take for this vibration to stop, for the energy to dissipate. And this is dependent on how strongly this proton is bound to its surrounding. And of course, in hexagonal ice, this happens very fast because the H1s are very strong, whereas in liquid water, this is slower. Because in the liquid phase, the hydrogen bonds are not that strong. And I can put this in numbers. I can show you that in ice, 0 degrees Celsius, this relaxation time is about 384 femtoseconds. This has been measured. Now, if you make a phase transition into the liquid water at 0 degrees Celsius, so no temperature change, just different phase, has a relaxation time of 740 femtoseconds. In between is the phase transition, meaning that by changing pressure or temperature, you can never get to a state of water that's in there because water is either liquid or solid, right? Or not, well, we'll see that. And if you increase the temperature, you get relaxation times higher than 740 femtoseconds. So you would expect the bridge to be somewhere around 800, 900 femtoseconds. It's not. It's exactly inside of the phase transition, closer to the liquid phase than to the solid phase, meaning that we have here direct proof that the hydrogen bond strength is increased, so this is actually on a molecular basis a state between liquid and solid. Now, knowing that, it's also easier to believe that the bridge exhibits properties of both the liquid and the solid state. And one of these properties, as I've shown you, is related to the way protons are carried across the bridge. Now, we have studied that using QENS, quasi-elastic neutron scattering. This is a technique where you send neutrons onto the bridge or onto your sample, and then you measure how much energy is transferred from the neutron to the proton or vice versa. And when you do that, you get an idea about how mobile is your proton in the system. And what I'm showing you here is the raw data, which cannot be evaluated as such, but just to give you an impression that even in the raw data, you see a much broader peak in the water bridge than you see in the reference water in the aluminum cylinder, which in this case is invisible to the neutrons. Of course, we also properly evaluated the data. And I should give you one example here for a specific angle. And you do this data evaluation by curve fitting. And the best fit that we had, for example, for this angle, was a combination of a Lorentzian and a delta function. Why is that interesting? Because a delta function is something that you don't get in liquids, ever. Liquids don't exhibit that because it's a total elastic reflection, more or less. Meaning that there's a small indication here that we indeed have a mixture or something in between liquid and solid here. And the Lorentzian is also interesting because from this width, from this half width at half maximum, we can actually calculate the diffusion coefficient in the system using the standard model that is used for water here, the random jump diffusion model. Now, when we do that, we get to this diagram. Now, follow me. The blue lines on the bottom here, this is liquid water. And you see that the dots, which are our actual experiment, are scattered. This is due to the fact that for this instrument, this experiment, you normally have a sample that's 5 by 5 centimeters and 0.1 millimeter thick. This is the optimum geometry. We can never ever get the bridge in that geometry. So what we did is we ran a sample with the exact same geometry of bulk water in order to compare. And you don't do that normally because then you get multiple scattering events. Neutrons are not scattered only once, but many times, and then you get this spreader of the data. Nevertheless, if you look at the green lines, this is the bridge, the water bridge, and the red line is the calculated version of bulk water at 50 degrees Celsius to be on the safe side, including multiple scattering. So even if we consider all the negative effects of the geometry, with the water bridge we are far, far above the value of bulk water. And actually, if you compare it in numbers, we are about 6 times higher in mobility for the second populations of protons in the bridge than we are in bulk water. Now you might think that if this is true, it's probably somebody else has found this before. It's always possible. This is a big world and there are many scientists. And it turns out that there's a number of papers from the 80s exploring the mobility of charge carriers, not being specific on what they are, in water using the application of high voltages, because water was used as dielectric in capacitors. And these papers were classified for some time. They have been declassified now. And the authors really found that the charge carrier mobility in there is about twice as high as it should be. Now we can use the Stokes-Einstein relation in order to calculate the proton mobility from the diffusion coefficient, and we get exactly, or more or less exactly, what these other authors 30 years ago found, which means that we can provide now a molecular explanation of the anomalously high charge mobility in distilled water when a high voltage is applied. Because back then the authors didn't know that water was in a different state when you do that. Next to that, we can calculate a number of interesting things. If you take normal water and you calculate the average jump length of a proton, you get to 1.6 angstrom, which is the nearest neighbor interaction, or as everybody of you, especially the chemists, know, the so-called famous Grotthuss mechanism. one molecule reacting with the next and the next and the next, nicely explicable with a ball and stick model. If you use the water bridge, the average jump length of a proton is 3 angstroms, which is a next to nearest neighbor interaction. So the protons, on average, skip one molecule when they interact. You cannot explain that with a ball and stick model of water. It's impossible. But you can explain this when you think of protons not as particles, but as waves. So if you think in quantum mechanical dimensions, then you could say this: the proton dematerializes and materializes again, or you could say a couple, very few, 3, 4 water molecules form a band structure in which the proton can travel. So this is not the same as a band structure in a solid state. This is why we didn't call it band structure. But it's also different from the normal liquid conduction mechanism. And this is why we called it proton channels, because the word channel was not used by solid state physics. Now, the final part of my presentation is, and I'm doing on purpose, I walk now here in front of a presentation. This is important. Look at this image. What do you think happens if you break the water bridge while it's running very abruptly? You put a plastic in between there. I've told you that at all times while it's operational, you have a surplus of protons on one side and a surplus of hydroxyl ions on the other side of the beaker. If you break the bridge, where do they go? Can they discharge into the electrodes? No, they can't, because the electrodes are electron conductors, but not proton or hydroxyl ion conductors. So actually, it's probable that they stay in the solution. Now, chemists will tell you this is impossible because then you would violate the law of electroneutrality. No, you don't, because the law of electroneutrality just tells you that the reaction as a whole has to be electrically neutral, and it is. But if you draw new system boundaries and you take it out of the equilibrium, you can end up with electrically, protonically charged solutions. And we have shown that by the means of electrical impedance spectroscopy. This is normal water. Nyquist plot, imaginary against real impedance. Very simple plot. There is a line missing, but it's just a capacitor and a resistor in series. Red line is the simulation. Black dots are the measurement points. So you see, we think we understand that. We can nicely simulate this. If you take the anolyte and the catholyte and you measure the electrical impedance, first thing that you see is, oh, they're different, which means that their conductivity is different. And in addition to that, here, there are very small features, not easily recognizable. I will magnify them soon. Tails, which are pointing clockwise and counterclockwise. And you can simulate that by adding circuit elements. In one case, an additional capacity, and in the other case, an inductance. And this is also known in electrochemistry. You do that when electrochemical reactions take place. Now, why would an electrochemical reaction take place when we measure the anolyte in electrical impedance? Well, in electrical impedance, what you do is you take a sample, then you run a current through the sample at different frequencies, and you measure the resistance, which is then the impedance. When you do that, you provide the systems with electrons. Now, imagine you really have free protons in there. The first thing the electrons would do is recombine with the protons and form hydrogen. And this is an electrochemical reaction. If that was true, then the second measurement would see fewer charge carriers and the impedance would increase. And it does. And then the third measurement, it increases again. So the more often you measure the same sample, the higher the impedance, because you're using up your free protons in solution by creating hydrogen. When we take a look at the catholyte, here also magnified, at first glance we would expect the same result, because here we are using up the surplus hydroxyl ions. But the situation is a little bit more difficult here, because the water which we're using doesn't have a pH of 7, it has a pH of 5.5, meaning that even in the neutral state, there is a much, much higher number of protons or hydronium ions compared to hydroxyl ions. So if you add any surplus negative charge in form of hydroxyl ions, you are just using up the protons which are in there, so you're using up charge carriers and you form water molecules. So if you take that charge out, what you actually should expect is that you increase the number of charge carriers because you free these protons, which are there from the carbonic acid equilibrium. You free these protons again, and you would create a smaller impedance. And this is actually what happens here. And you also see the chemical reaction, which is taking place, and which creates oxygen in this case. This is a summary, and interestingly, whereas we had water in the beginning when we put it into the beakers, when we break the bridge and analyze the content of the beakers, this is not water in the common sense anymore. It's not H2O. We calculated it. It's H2.00000000045 O delta plus, and H1 point, a couple of nines, H6 O delta minus, with an effective net charge of about 5 millicoulombs per liter. Now this is really low. You know these small batteries, they have 1,800 milliampere hours. A coulomb is a milliampere second. So we are 4 to 5 orders of magnitude away here from actually creating a useful charge storage system. But nevertheless, we did it. We created water that is electrically charged, both positively and negatively. So to summarize, the floating water bridge resembles a protonic resistor. We've established that. We know that it heats up the water bridge because of the electrical current, and also, I haven't shown you that, but this extra peak in the infrared spectrum that actually comes from this protonic band transition, which can be calculated if you apply the band structure of the OH oscillator. Protons are generated by electrolysis and in the anolyte and neutralized in the catholyte. We have seen that. The water in the floating water bridge is in an electrically excited state with increased H-bond strength. And this is inside the no man's land of the phase transition between ice and liquid. And in this excited state, the protons reveal an increased mobility and traveled through so-called proton channels. And finally, because it's a protonic resistor, if you break it, you can take the system out of the equilibrium and create electrically or protonically charged water. At this point, I would like to thank many people. First of all, Professor Jacob Wojciechläger from the Technical University of Graz, my mentor and the big man behind the water bridge, who never shows up in public, almost never. But without him, I wouldn't be standing here. And I would also like to mention my friend and colleague, Adam Wexler, who just successfully finished his PhD on this topic. Many other people around the world who made this possible. And of course, the AWP, Applied Water Physics companies who sponsored this research should be named here, alongside with WETSUS, which allows me to continue with this investigation. And finally, I would like to thank you all very much for your attention. Oh, this is the ISIS of Alan Soper in Oxford.
That's open for question. First, Romiana.
Thank you very much for the, as always, beautiful presentation, very impressive. I have one question and one comment. The question is, have you tried to get the same bridge in different, not in cylinders, but in something with parallel walls? Have you tried different forms of the beakers?
I can show you. I thought I did. This is very quick. This image, this was done in cuvettes, rectangular shaped cuvettes.
Okay, great.
And the bridge hates that because the electric field at the corner is concentrating. It's very unstable. The cuvette has the advantage that you can do Schlieren imaging, which is beautifully done here. So you see the water flow, but if you try to establish a bridge, it will break down, it will run around the corner. So yes, we have, and it's really, I wouldn't advise it.
Okay. Now, you're talking all the time about liquid and ice. I think you have, in principle in water, we have all the time, simultaneously, vapor as well.
Of course.
Your vapor is not only above the bridge or beside the bridge. Water vapor is in the water. And I think all the dynamic changes that are obvious in the bridge are caused by the vapor in the water. And it could be followed by spectroscopy, by imaging spectroscopy, probably.
Okay.
When you could see with infrared, you can do it very easily, because you could identify different water structures, like hydroxyl on the top of different conglomerations of water molecules. And then you probably will have a brilliant idea what is your proton flow in this cuvette, beautiful cuvette.
Well, thank you very much for this. I have to admit, of course, when we saw the vapor lines in the spectrum, we naturally assumed it's the vapor above the bridge. And you can also visualize that. But there's no proof whatsoever that the vapor is not, although I cannot imagine how, but it could be inside of the bridge.
Yeah, if you analyze your spectra, you will definitely find it. Yeah.
Thank you.
Have you noticed that the volume of the beakers changes during the electrolysis? Because you might have some kind of electroosmosis there.
The bottom of the beakers?
The volume, the level.
Of course, yeah. It goes up and down, up and down. There is it's an equilibrium. There's always a little bit more water in the catholyte than the anolyte, but it stabilizes. Mm-hmm. It's an electroosmotic flow, yes, absolutely.
Okay.
Absolutely.
And a second question, have you explored the relevance that may have these results in terms of in biology? Because there is an old theory of Mitchell that is treats with the transference of protons in order to obtain ATP. Have you explored that possibility?
We have not explored that. What we did, and what we're still doing is, because it's very difficult to measure the water in the cells for us, what we did do is we added bacteria and other microorganisms to the system and studied their behavior. There's one paper already published about that. It's quite astonishingly, most of the E. coli which we used survived. They even showed increased metabolism. And there's another paper with a lot of other species which is now under review.
Excuse me.
Yes.
The discovery of the transport of cations through the water bridge.
Discovery of the transport of?
Cations.
Cations, okay.
Cations. Through the water bridge.
Yeah.
Was made by my colleagues and me in 2007. And you were informed by Emilio Del Giudice. So
I'm not following. Oh, we have not seen any cations going through the bridge except for protons.
Yes, but the basic physics is the same. We discovered the transport of cations of copper. And so I think that you should quote not only Lord Armstrong, but also us when you present or introduce the transport of cations. Thank you.
Thank you. Yeah, I would like to answer to that. We are actually not investigating solutions. Actually, we never did, except for organic solutions, because if you add ions to the system, it becomes extremely unstable. But I would love to see the paper you're talking about, because I'm unaware of it.
Thank you. Thank you, Elmar.
Thank you.